So, if computer scientists are kind of pessimistic that we'll be able to find an exact algorithm that's efficient, the kind of next natural step is to try and see if we can approximate something efficiently. So, maybe the true solution is really like a 100-mile trip, but maybe you can come up with an algorithm that's fast that maybe always guarantees that it's always at most 5 miles more or something like that. In which case, you can get a really good approximation in a tractable manner, and one that you can actually find a solution for without having to wait 130 years. And that's the kind of key idea behind this whole study of approximation algorithms, trying to approximate whether or not a solution to a problem in order to gain efficiency. So this is the idea of kind of, if we don't think we can solve something exactly in an efficient manner, maybe we can something that's close enough is a good idea. So this is kind of what I was saying here, where an approximation algorithm would hopefully find a solution that's close to optimal while not having to spend as much time. So one of the key aspects of an approximation algorithm is its approximation ratio, which is how far off from the real solution are you allowed to be. So we'll come up with an algorithm that approximates TSP, and it'll print out a solution path P, and we want to compare it to this kind of optimal solution that we would have to use an exact algorithm for. We call that P star. Now, we usually talk about there being some kind of approximation ratio, some variable alpha, where we say the cost of our path is going to be less than or equal to alpha times the cost of the optimal. For example, when we talk about, and if this alpha ratio exists, then we call this an alpha approximation algorithm. So for example, a 2 approximation, if the true solution was 100 miles, then a 2 approximation would find a path that's 200 miles or less. So the idea being that it's going to find something that's close-ish, but no worse than twice as bad as the true optimal. If you got a 1.1 approximation, then your approximation would always be at most 1.1 times the optimal. So in that case, if a 100-mile example, then our approximation would always be 110 miles or less. So the idea is we're trying to get as close as possible to the optimal. And so the lower this alpha term is, the better your approximation will be. Now, we're not going to talk about any algorithms today that have this quality I'm about to describe, but a lot of these approximation algorithms usually take alpha as a parameter, where you say, oh, you want to make a 2 approximation? I'm going to have to spend a little bit less time than if you were going to want, say, a 1.1 approximation. So there are lots of approximation algorithms for different problems. And some of them take this kind of what level of approximation do you want as a parameter, and will usually spend more time to get a more exact result. But we won't talk about any of those algorithms today. So let's talk about our first approximation algorithm. We're going to use a kind of non-obvious application of minimum spanning trees to solve the traveling salesman problem. So use an MST to approximate TSP. So here's the description of how this works, and I'll walk through an example. Start by running prims to find a minimum spanning tree. Then trace through a DFS of this tree to explore the graph, and then do something about skipping vertices you already visited. So we start, and this will hopefully form a cycle over the whole graph. Now, here's how this works. So we start by running our minimum spanning tree algorithm. We get a minimum spanning tree. Then we run a DFS on this tree, so a depth first search. And I use this word trace to highlight that it's going to be kind of a modified DFS. The idea is, as you're traversing, you print out nodes the first time you visit them, and the last, like every time you visit them on the DFS. So for example, doing a DFS trace from this the start vertex A, we could do something like go to A, I should use my mouse, go to A, then to B, then to C, then to D, and then back to C, because we have to go back. Whenever we do this DFS, we've explored all the children, come back and explore the others. We'd print out C again, then E, then C, then B, then A. So this trace is just the DFS, but being really explicit every time you like look at a node, even if it's kind of a node you're kind of currently exploring all of its children of. So then we cross out all the duplicates in this trace. So since we already visited C, remove it. And since we already visited C and B, remove that. And then we use this ordering of the vertices to determine our cycle. So we'd say that our proposed shortest path goes from A to B to C, I forgot D in there, I'll fix that in the slides, from C to D to E to A. So it kind of goes around the outside. Now this turns out to have a total cost of 24. And it turns out in this example, this is actually the shortest path for a traveling salesperson problem. Now, this isn't always guaranteed to find the exact shortest path, but my argument is that it approximates it in general. So, how good of an approximation does this do? I can't really prove to you that this algorithm works. It does, but it's not going to find the optimal, right? It's going to find a cycle that is hopefully not too suboptimal. And so, if you go through the math, it turns out that this MST approximation ends up being a 2 approximation of that kind of minimum traveling salesperson problem. So no matter what the optimal solution is, this algorithm will always find one that's no worse than twice as bad. And so I was using that 100-mile example is the true optimum. This algorithm will always spit out a path that's 200 miles or less if the optimal is 100. Now, the reason why this algorithm works, or tends to work, is in most cases, should be a lot of overlap between a minimum spanning tree and a traveling salesperson's path. Why? Well, because the minimum spanning tree is a tree that covers the entire graph that uses all the minimum edge weights. And so there should be a lot of overlap there when getting between two cities has a really short edge weight. And so we would hope there that this minimum spanning tree has a lot of overlap. And this kind of tracing and skipping is just skipping nodes we already visited. And so that's going to make the solution slightly worse, but does now find this kind of nice cycle. So again, I can't argue to why this actually is a 2 approximation. I'm going to link to a resource that does do this proof if you're interested. But the key idea is people realized that there should be some overlap with minimum spanning trees. And they tried, can we use that and make a modification to the algorithm to get us a solution that's not perfect, but close? And notice importantly that in this approximation case, we said that the solution to the approximation is less than or equal to alpha times the optimal. It's okay if sometimes it finds the optimal. We're just saying that in the worst case, it's not going to be too far off. In this context, saying that twice as bad isn't too far off, which may or may not work for your context. So kind of a natural question to follow up with is, can we do better than a 2 approximation? Is there an algorithm that has something closer to 1, something that's much, much closer to the actual optimal? And that is what we'll talk about in our next video.